Alright everyone, so today we are going to start on chapter 3. In this chapter we're going to talk a little bit about types of molecules, how to name them, ways of representing chemical compounds. And this will be kind of an extension of what we've been talking about. So in the last chapter we talked about sort of the origins of the atom, what it's made of, types of elements, that kind of thing. Okay, so now today we're going to take those elements, those atoms, and put them together into some molecules. Okay, so this one is kind of a nice chapter because we get to sort of relax from all the math we've been doing. And this one will really be more conceptual than anything, and I think it will start to feel a lot more like a chemistry class to you than a sort of a math class, you could say. So hopefully you'll like this one. Let's go ahead and get started with it. So first thing we're going to talk about is water. Okay, so we're going to start from sort of just an example compound. Hold on, that's not the slide I want. Okay, so we're going to use water just as an example compound here. Okay, just to sort of frame what we're talking about a little bit. Okay, so the first thing we're going to talk about is that elements combine to form compounds. So when we talk about a compound, this could be any chemical compound. So it could be something like water, it could be CO2, nitrogen, anything like that, anything you can think of that has multiple atoms that are combined together. Okay, that's going to be an example of a compound. And these are based on two things we talked about last time. Okay, so if you remember back to Dalton's atomic theory, we talked about law of definite proportions. Okay, so this tells us that when two things form a compound, okay, they're always going to form the same ratio. And if they don't, so then we have multiple proportions. If they don't combine in that same proportions or that same ratio, okay, those are going to be different compounds. So the example we used a lot was something like CO2 versus CO. Okay, so these are two different compounds. One is carbon monoxide and one is carbon dioxide. And we're going to talk about in this chapter where we get those names from and how exactly do we name things, and certain types of compounds are named in different ways, and we're going to get into that. Okay, but first let's just look at our example compound here, water. Okay, so we know that water is made up of oxygen and hydrogen. Okay, so in this column we have hydrogen, and over here we have oxygen. Okay, then we just have some properties down below them. Okay, and the point of this is to say that when two atoms combine to form a compound, if you see what it says here, the properties of that compound are completely different or totally different, they say, from the constituent elements. Meaning that when two things come together to form a compound, it has its own set of properties that aren't necessarily those of the two atoms that come to combine it, or to combine to form it, I should say. Okay, so let's look at it. So the first thing we have is boiling point. Okay, so we're pretty familiar with hydrogen and oxygen just in terms of something like this. For instance, we know they're a gas at room temperature. Okay, the boiling point is minus 253 C, and for oxygen, minus 183 C. So these things boil at a very low temperature. So they're going to be gases at room temperature, so we know that. Just inherently, you know oxygen is in a gas, and it's a good thing because we need it, right? Okay, and if we look at their properties, okay, we know that hydrogen is explosive. And then in order to have a combustion, we have to have oxygen. So anything that burns is just really, what you're doing is you're combining it with oxygen. So that's why it says here, necessary for combustion, because it's required to burn something to have oxygen. And we'll get into that later when we talk about combustion. But the point I'm trying to make here is that if we take a look at the properties of water, okay, again, something we're pretty familiar with. Okay, we know that water boils at 100 degrees C. We know that it's a liquid at room temperature. But think about this for a second. Isn't it interesting that two things that combine to make water, so we have H2 and O2 come together to make H2O. Now, isn't it interesting that those two things on their own are flammable, but what do we use to put out fire? We use water, right? So it's used to extinguish flame. So I think this is hopefully a good example to kind of keep in your mind that when you're thinking about forming compounds, or when you're thinking about two atoms coming together to form a compound, just remember that the properties of that new compound are not necessarily the same as the properties of the things that come to combine it. Now, they may share some characteristics, sure, but not necessarily either. Okay, which is kind of a weird thing if you think about it. You would kind of expect it to almost be, like for instance, the boiling point. Maybe you would expect it to be, I don't know, minus 200 C. But that's not what we see. And I just, hopefully that, that conveys the point of, just remember when you start to form compounds, okay, they're probably going to end up having different properties. Okay, so hopefully that will kind of stick with you. Okay, so how do we make compounds in the first place? So we said two atoms come together to form that compound. What really do we mean by that? Well, of course what we mean is that we've formed chemical bonds. And we'll talk a little bit about the types of chemical bonds. So compounds are made of atoms held together by chemical bonds. Of course, right? We have all heard of chemical bonds before. But what really is a chemical bond? So a chemical bond is the attractive forces between two atoms. Or it could even be more than two. Okay, but the bonding attraction comes from two things. Okay, it comes from the attractive forces, the attractions between protons and electrons. So remember, these are positive, these are negative. So just like two poles of a magnet. Okay, so that electrostatic attraction. Okay, so it comes from the attraction between the protons and electrons. And it doesn't mention this in this slide, but it's also a balance of the repulsion of two electrons. Because remember, these are similarly charged. So just like the same poles of a magnet or two magnets, they're going to want to push away. So a chemical bond is really, okay, it's a delicate balance of these two forces. Okay, so we have a positive attraction, we have a positive and negative attraction, and we also have repulsion between similar charges. And of course the same is true for two protons as well. Okay, so they're going to push away too. Okay, so a couple types of chemical bonds. Okay, so the first one, we have ionic. Okay, so this is between a metal and a non-metal element. Okay, so an example of a very common ionic bond would be this, sodium chloride. Okay, and we'll get into why we call that an ionic bond, or what separates it from the other bonds in just a little bit. Okay, the second type we have is a covalent bond, and this is between two nonmetals. Okay, so for instance, let's just say methane. Sure, that's a simple one. Okay, so those are two nonmetal elements. Okay, so that would be a covalent. Okay, and we'll talk about what makes a covalent bond different than ionic bond as well. The last one, not quite as common. We'll touch on this a little bit, but it's not something you need to know quite as much about. But the last one is metallic. Okay, and this is between two metal elements. And pretty much these are kind of rare. You won't see them as much, but it's good to know they exist. Okay, so unless you maybe got deep into inorganic chemistry where you're really going to talk about this type of bond, is probably not one most people have ever even heard of. Okay, so just keep that in mind, but just know that it exists for now. Okay, so the first one we'll get into is ionic bonds. Okay, and what makes an ionic bond different, or what makes it unique, we could say. Okay, so an ionic bond, again, is occurs between a metal and a non-metal. Okay, so remember all your metals on your left-hand side of your periodic table. So that includes everything from, lithium all the way over to something like aluminum. Okay, then you have the transition metals in between. And your non-metals are going to be on the right-hand side. So things like your halogens, your oxygen, nitrogen, carbon. Right? So those are all your non-metals. An ionic bond involves the transfer of electrons from one element to another. Okay, so what we need a positive, usually the metal, and we need a negative, usually the non-metal. Okay, when those two things are around each other, they come together to form an ionic bond. And this is just a bond that occurs, again, between a metal and nonmetal, strictly because one is positively charged and the other is negatively charged. Okay, it involves the transfer of one or more electrons from one element to the other. And generally speaking, it's going to be from metal to the nonmetal. Okay, the ionic bond results in the attraction between two charges. Okay, the positive and the negative. Easy enough. Okay, over here we say a cation plus an anion. Okay, positive and negative. Okay, the resulting cation and anion are attracted to each other by electrostatic forces. Okay, just meaning literally similar to electricity, you could say, electrostatic. So it's just that positive and negative attraction. Okay. I'm going to say that these are governed by Coulomb's law. Okay, and the strength of the bond can be calculated using Coulomb's law. We'll touch on that. Okay, compounds formed having ionic bonds are referred to ionic compounds. Of course, right? Easy enough. Okay, so here's an example. Okay, an example of that sort of how an ionic compound might be formed. Okay, suppose we wanted to make sodium chloride. So sodium chloride is just table salt, regular old table salt. Okay, and we see like sort of a close-up image of that here. So one thing kind of interesting before we get into the science behind it, one thing kind of interesting is that if you notice, table salt is cubic. Okay, so it forms perfect little cubes. So if you were to, at home, take a bunch of salt, so like maybe, I don't know how much, maybe half a cup or something like that. Okay, and put a little bit of water on top of it. You know, make sure that it's all dissolved and let it sit maybe on your kitchen sink or a windowsill, something like that. Okay, what you'll end up with after several weeks or months, okay, you're going to end up with perfect little cubes of salt. And you don't have to do anything except wait. That's just its nature. Okay, well, so if that sort of thing kind of interests you, that's more like the inorganic side of things. Anyway, so back to my point. Okay, so if we're going to form table salt, okay, we're going to form that from sodium metal and chlorine gas. So when you buy sodium metal, it looks something like this. It comes in little bricks. Okay, and that's something that's so common to us, sodium, we don't ever really think of it as being a metal anymore, but it is. So the lab that I worked in, one of the things we did was dry solvents and things with sodium metal. So we would have, it comes in an oil, and you cut it and you wash it, and it will react with the water and the oxygen in the solvent. So something like hexane, for instance. Okay, and it will actually remove the water. Okay, so it'll form sodium hydroxide, which will settle out. Okay, but this is how it looks when you buy it. Usually it's kind of has like a coating around it, and you have to cut that off. You don't need to know that. I just think it's interesting. Okay, so sodium metal, you cut a chunk off, and you put that in the presence of chlorine gas. So chlorine gas has sort of this yellow color to it. Okay, so this is just Cl2, and this is Na. Okay, so this is going to be a solid. This will be a gas. Okay, so if we put these two in the presence of each other, so we put them, maybe we drop a piece of sodium into this flask. Okay, what's going to happen is an electron is going to transfer from sodium over to chlorine. What we're going to end up with is this. So Na plus, Cl minus. Okay, and those two together will form an ionic bond. And if you notice, metal compounds like to sort of come, or ionic compounds like to come together like this. So you kind of have this repeating pattern. Okay, and depending on what compound it is, the pattern could be different. Okay, so here we have chlorine, a little bit bigger, which is the green, and the purple is the sodium. And you'll see that pattern repeat over and over and over if you look. So here's all your sodiums, and it's just repeating. Okay. So those two come together, transfers an electron, and you form sodium chloride. Okay, and then again, they're held together simply because one is positive and one is negative. Okay, so here's a problem for us to try. And I know you don't know how to do this yet, so I'm going to use this problem as an example of how to do it. Okay, so let's write the formula for the ionic compound that forms between calcium and oxygen. Okay, so let's just walk through this one together. Okay, so all we want to do is we want to write the formula for whatever compound we would think would form from carbon or calcium and oxygen, excuse me. Okay, so the first thing we want to do is go to our periodic table and we're going to find our two elements. Okay, so let's look for our metal first. Okay, calcium. So we come to group 2 here, there's calcium. Okay, then oxygen, we know is going to be over here on the right-hand side, and it's right there. Okay, then we want to write the charge that's generally associated with those. So I know if I'm in group 2, it's going to be 2 plus. And I know for oxygen, it's going to be 2 minus. Okay, easy enough. And we can just write that out like this. Okay. So then what we want to do is we want to just write those together. Okay, so we have calcium, we have oxygen, so forget anything else and just copy them and write them next to each other. Leave a little space in case you need to write a subscript. Okay, and what we're going to do is this is called the crisscross method. Okay, so if I know the charges, what I can do is this one will go here and this one will go here. So what you end up with sorry. I thought maybe I had it written here. Okay, so what you end up with then, if you just copy the numbers down, you would end up with this. Okay, but if you notice, 2 and 2 are the same. So if I can reduce it, I should. Okay, so I'll cancel this with this. In other words, just divide both by 2, and you end up with this, CaO. And the last thing you want to do is just make sure everything's balanced. In other words, make sure the charge is neutral. So I have 1 calcium that has a 2 plus charge. That gives me 2 plus. I have 1 oxygen that has a 2 minus charge. Gives me 2 minus. Okay, so I have 2 plus, 2 minus. Those balance each other out. Okay, so that's all there is to it. And if I had some other element here and I couldn't reduce the numbers, you just stick with those numbers. Okay, but again, always make sure that you're balanced in the end. And we'll do some of these. Hopefully you'll get the hang of it. Next type of bonding we'll talk about is covalent bonding. So this is bonding that occurs between 2 nonmetal elements. Okay, so this arises from the mutual attraction of 2 nuclei for the same electrons. Okay, so what ends up happening with this is what we call electron sharing. Okay, so we have 2 positively charged nuclei, okay, both sitting sort of in proximity, let's say, and they both have electron clouds. So what's then going to end up happening is that both of those nuclei will have attraction for the same set of electrons. So, one element's attracted to the other element's electrons or atom's electrons, and the other atom is attracted to the atom's electrons. Okay, so this is sort of what I was talking about before. Okay, so when we're talking about ionic bonds, so if we go back just a little bit. Okay, so here I started talking about sort of the balance between, okay, so this is what we were talking about. So chemical bonds. Okay, so remember we talked about it being attractions between protons and electrons. That's true, yeah. And then we started talking about the fact that it's actually sort of a balancing act. Okay, so that's what we're getting into here. Okay, so it's a bond is a balance between the attractive forces, okay, so protons from atom A to the electrons of atom B. So there's a balance between attractive forces and repulsive forces. Because remember that the light charge is still going to repel each other. So the electrons of atom A repel the electrons of atom B. The protons of atom A repel the protons of atom B. So what has to be true is that the attractive forces have to outweigh the repulsive forces. So atoms only want to get so close to each other. Okay, so at some point we'll talk about bond lengths, and you may wonder, okay, well, why isn't the bond length between two atoms 0? Wouldn't they want to be right next to each other? And that's logical, but the reason that isn't true is because of these repulsive forces. Okay, so they actually push away from each other too. Okay, so there's sort of a like happy medium, you could say. So there's just a balance. There's a balance between the two atoms. Okay, so covalently bonded compounds are referred to as molecular compounds. Okay, also sometimes referred to as molecules. Okay, so if I were talking about a molecular compound, that's going to be covalently bonded, as opposed to an ionic compound, which would be ionic bonds. Okay, and one way we represent chemical compounds is through a chemical formula. Okay, so a chemical formula represents the composition of a substance. So it indicates the type and the number of the elements that make up the molecule. Okay, so it's going to tell us what's there and how many. So an example here, C2H6O. Okay, so this is the chemical formula for ethanol. Not really important what it is. Just here's an example of a chemical formula. Okay, so ethanol is composed of 2 moles carbon atoms. So remember we talked about the mole. 6 moles of hydrogen atoms. And 1 mole of oxygen. Okay, so these numbers indicate not only how many atoms are there. So if we're talking about one molecule, then yeah, sure, we could say this is number of atoms. So we could say it's 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. Or you could look at it this way. So it's actually the number of moles. Okay, so it represents both things. Okay, so it simultaneously represents the number of moles of carbon, moles of hydrogen, moles of oxygen. So what ratio are they in? It can also represent the specific number of atoms in a single compound. Okay, and if we want to know the molar mass, or here they say molecular mass, those two are virtually interchangeable. Okay, so if I want to know the molecular mass for ethanol, okay, we use its molecular formula. Okay, so it has a mass of 46 grams per mole. And 1 mole of ethanol has a mass of 46 grams. So those are saying the same thing. So it's 46 grams per 1 mole, and 1 mole of it has 46 grams. Okay. And we'll talk about how do I find that out. I don't think it's quite yet, but it's coming up. Okay, so types of chemical formulas. So molecular lists the exact number. So if we're talking about a molecular formula, lists the exact number and types of atoms. Okay, so example, hydrogen peroxide, H2O2. Okay, so when it comes to talking about molecular compounds, we're not going to reduce these numbers, even though we could. Okay, if we're talking about molecular formulas. Okay, but the other one is empirical. Okay, so empirical lists the relative type and number of atoms in the compound. In other words, it's going to tell us the simplest whole number ratio. Okay, so if I can reduce any numbers, for instance these 2's, I will do that to get to empirical formula. So it's the simplest ratio. Okay, so for example, we use our example hydrogen peroxide. So we have H2O2. So if we want to get to an empirical formula, what we're going to do is we're going to reduce those 2's. So just divide both by 2. And what we end up with is HO. Okay, so that's our our empirical formula, our empirical formula for hydrogen peroxide. And notice they indicate N is equal to 2. So they write an N and then say N equal to 2. And that lets the person know that if I want to get back to the molecular compound, or the molecular formula, I multiply it by 2. Okay, so if I multiply HO by 2, I get back to H2O2. Okay, so what this tells me is that for every hydrogen present, there's 1 oxygen present as well. Okay, so it just tells me the ratio. It doesn't tell me the exact numbers. It just tells me that it's a 1-to-1 ratio. Whereas with H2O2, I know, okay, no, it's 2 hydrogen and 2 oxygen. Okay, so that's the big difference there. The last one is structural. Okay, so the structure represents how the atoms of the molecule are connected to one another. Okay, so for instance, if we were talking about something like ethanol, I might write a structural formula like this. So C3, CH2. Then over here I might write OH. Okay, just indicating that's an alcohol. So instead of writing C2H6O. Okay, so this doesn't tell me anything about the way that the molecule is actually shaped. But this, writing the OH at the end, shows you right away that it's an alcohol. Okay, so sometimes you'll see this. And there's other types of structural, but this is one. So if we're just using letters and numbers, this is one type of structural formula. Okay, so getting back into empirical formula. So empirical formulas do not give information about the compound's shape or how the atoms are attached to each other. The empirical formula may or may not indicate how many of each atom are present. Okay, so sometimes what that's saying is sometimes the empirical formula and the molecular formula are the same, and other times they're not. Okay, so if the molecular formula and the empirical formula are the same, it will tell you how many of each type of atom. But if they're not, it doesn't do that. So will if the molecular formula is the empirical formula, so sometimes they're the same, will not if the molecular formula is a multiple of the empirical formula. Okay, so here we have oxalic acid, C2H2O4. The empirical formula for oxalic acid is CHO2. So notice, again, we're just reducing by 2. It won't always be 2s, but again, another example, we're reducing by 2. Okay, so that's the empirical formula, CHO2, just reduced by 2. Here with the molecular formula oxalic acid, C2H2O4, which is 2 units of the empirical formula. Okay, so we just multiply by 2 to get back to the molecular formula. Okay, so an example of a question I could ask you about this, I could ask you to just write out an empirical formula. I could give you a molecular formula and ask you to find the empirical formula. That could be an example of something like this. So just remember, you just reduce it to its simplest form. Okay, so what about other types we can represent something like oxalic acid? Okay, so we have our molecular formula. Good. Empirical, which again is the simplest form. Okay, so just reduce it down to its simplest form. Okay, and the last one is structural. Okay, so I told you there's sort of multiple types of structural formula. This is another one. Okay, so this tells me exactly how every atom is connected. So if I was, for instance, just to give you this, unless you're familiar with oxalic acid, you may or may not know that it's connected this way. And most likely you wouldn't, because who just walks around, right, in their everyday life thinking about the structure of oxalic acid? Probably not very many people. Okay, but if I give you this, then you have some idea how it's connected. You know that there's, for instance, you know there's double bonds. You know there's an OH bond. Sorry, sometimes when I get going, I touch my screen and it makes it advance the slide. Okay, but you know that there's a carbon-carbon bond. You know there's a COH bond. Okay, so this gives you all of that information combined. It also tells you what types of atoms are there, how many of them, and it shows you how they're connected. Okay, so here's a problem for you to try based on what we just talked about. Okay, so it says determine the empirical formula for the following. And it gives you a 1, 2, 2, and 3. So an ionic compound that has 2 aluminum ions for every 3 oxide ions. Hexane. And the last one, arabinos. Okay, so go ahead and give this a pause. Try to write these out. Okay, even if you're wrong, that's okay. Just give it a try and see what you come up with. Okay, and when you pick back up, we'll go over it together. Okay, so let's take a look at this one. So the first one says, an ionic compound that has 2 aluminum ions for every 3 oxide ions. Okay, so let's just write what it says. So we're just looking for the empirical formula. So all I want to do is literally just write what it tells us. So the first thing it says, aluminum. Okay, so Al. Okay, it says we have 2 of those. Next thing it says, we have 3 oxide ions. Oxide is just oxygen turned into an ion. It says we have 3 of them. Okay, that's it. That's your empirical formula. We can't reduce it any further than that. Okay, so that's our empirical formula. Okay, the next one, hexane. So here we see C6H14. Remember, we're looking for empirical formula here. In other words, we just want to reduce these as much as possible. Okay, so we could maybe divide by 2. Let's try that. So C3H7. There we go. And I can't reduce that any further, so that's my empirical formula. Last one, we have C5H10O5. Okay, so I see a lot of 5s in there, and I see a multiple of 5. So let's just reduce by 5. Okay, so we'll say CH5O. Okay, that's it. So that's our simplest form. I can't reduce it any further. Okay, so that's going to be our answers. Okay, let's check. So Al2O3, got that one right. And then here, I didn't do this, but one thing you can do, of course, is to, and this you would want to do this. You would want to do this, so write the N, and say N equal to 2. That way people know. Okay, and the same thing here. So we would say N, and then N equal to, oh sorry, this should be a 2. N equal to 5. Okay, and so those are our answers. We've got them all right. Good. Okay, the next one. So it says write the empirical formulas for the compounds represented by the molecular formulas. Okay, again, give this one a try. So this is the molecular formula. They just want you to write the empirical formula. Let's give this one a try real quick, and when you come back, we'll go over it. Okay, so the first one, see C4H8. Okay, so I could easily reduce this by 4, right? So I could say CH2. Okay, where N equal to 2. Oh, sorry, to 4. Sorry, that's an N. Might not look like it. Okay, next one, B2H6. Okay, we easily reduce by 2. So we'll just say BH3. N and N equal to, what do we say, 2. Okay, next one. Okay, so here we have CCl4. So is there anything we can reduce this one by? So we can't reduce by 4. That would give us C1/4 Cl. Okay, well, divided by 1 doesn't do anything. Okay, so no reason to do that. So this is, in fact, our empirical formula already. Okay, so sometimes they are the same. Okay, we can check our answers real quick. A, common denominator is 4, so CH2. Okay, that's what we put. Common denominator is 2, so BH3. I'm going to erase this so it's not on top of all the writing. Okay, and then the last one, common denominator is 1. Okay, so it just stays the same. Okay, so hopefully those are pretty easy for you, just reducing the number to its simplest form. Okay, so let's take a look at some more ways to represent compounds. Okay, so these would be sort of more like, you could call them models. They could be kind of an extension of structural formulas. Okay, but the point is that these give us more information about the way the atom is put together, or the molecule is put together, I should say. Okay, so one is the ball and stick model. Okay, so this uses balls to represent the atoms and sticks to represent attachments, in other words, the bonds. Okay, and more than likely you're going to see gray as carbon. Sometimes they're more closer to black than gray, but one of those two shades will represent carbon. And then the white is almost always hydrogen. And this is common throughout chemistry. So if I showed this model to another chemist in another country, they would most likely know what I was talking about. Okay, the next one is space filling. Okay, this uses interconnected spheres to show the electron clouds of the atoms connecting together. Okay, so this one is the ball and stick. Okay, so it just shows us what atoms are there and how they're connected. So this tells me I have a carbon with 4 hydrogens attached. Okay, so these all 4 represent the same molecule, CH4. Okay, so this one tells me that there's carbon and 4 hydrogens. Okay, so it tells me exactly what the molecule is, but it doesn't tell me anything about the way it's shaped or the way that the bonds are connected. Now, with methane, there's only one way to arrange it, okay? But there could be, multiple types of arrangements you can make with any one molecular formula. So if I need to know more, I'll use the structural formula, so CH4. Okay, so now I know that every carbon, or that this carbon has 4 hydrogens attached to it. Okay, so I know exactly how it's shaped. Okay, but something this one doesn't tell me is the 3D spacing of it. So it tells me how they're bonded, but it doesn't tell me about how it looks in actual 3D space. Okay, so in all reality, well, let's just say on paper, this appears to be all in the plane of the board, or on the plane of the paper, you could say. In other words, it appears to be a flat molecule. But in reality, methane is not a flat molecule. Okay, so it has what we call a tetrahedral shape, and that's something we'll get into later. Okay, but so this is how it actually exists in 3D space. Okay, so if we want to know exactly how the molecule is shaped, we'll use the ball and stick model, and there's even little modeling kits you can use to put these together. Okay, and the last one is the space filling. Okay, so that's this one, and it represents the same thing. Okay, so carbon in the middle, 4 hydrogens. Okay, so nothing's changed about our molecule. But the good thing about these is if I need to know something like a cavity size, for instance, like how could a molecule fit inside of another molecule, which is a real thing, that especially if you're an inorganic chemist looking at combining metals with ligand compounds, that's something you would think about. Okay. So maybe I want to know that information, and for that case I would use the space filling model. It basically just shows me how big the electron clouds are. Okay, but the important things about this is that they represent the 3-dimensional structure. Okay, so it gives me the idea of how it's actually shaped. So the structural formula just shows me how they're connected. The ball and stick and the space filling actually show me the shape of the molecule. Okay, so here's some examples, and we don't have to go through every single one of these, but you can kind of get the idea. So here we have benzene, molecular formula C6H6. If I reduce that by 6, I get the empirical formula CH. Structural formula, okay, so benzene is a ring with double bonds in it, a ring of carbon with double bonds in it. Okay, this ball and stick, very similar, so it just so happens that this is more like a planar compound. Okay, no problem there. And then the space filling model shows that there's really not a lot of space in here. It's pretty much all filled up by those electrons. Okay, what about one? Let's look at the bottom one here, ammonia. Okay, so NH3, NH3, so empirical and molecular formulas are the same. Structural model, NH3, so it appears to be a planar molecule. Okay, but if we were to put a model together to represent this compound, you actually see that it's actually shaped closer to methane than it is something like benzene, for instance. So it's not a planar molecule. So you notice that these are actually pushed down away from the top. And the reason is that there's a lone pair there. Okay, but you don't need to know that for right now. Okay, the point is just to understand the different things that these models tell you. Okay, they're all good in their own right. It just depends on what information you need. Okay, so you can look at these closer if you would like, but that's enough as far as I'm concerned for now. Okay. So classification of elements and compounds. Okay, so compounds composed of a metal and a non-metal element are ionic compounds. Okay. So the cation and or anion may be simple, or they can be polyatomic. And I'll tell you what I mean by polyatomic in just a minute. Okay, so some examples could be chloride ion, okay, copper 2 ion, silicon 4, okay, Si4 plus, nitride N3 minus, okay, or they could be polyatomic. Polyatomic, so poly, meaning many, and then we have atom. Okay, so literally just means many atoms. Okay, so an ion can come together or can be formed by several atoms rather than just by one or two. Or rather than just by one. If it could be just two for a polyatomic. Okay. So an example of a polyatomic ion here would be nitrate. Probably something you've heard before. Probably referring to something like fertilizer or something like that. Okay, so nitrate ion is NO3-. So this whole thing has a negative charge. It's not just localized on one particular atom. We have to take the whole thing. Okay, so the whole thing, NO3-. That's the polyatomic ion. Okay, or we could also have the ammonium ion. Okay, so if we add an extra proton to ammonia, we get ammonium, NH4. So this whole thing has a +1 charge. Okay, and remember we talked about that. If something is composed of only nonmetal elements, it's a molecular compound. Okay, and these are attached to each other through covalent bonding. Okay, so that sharing of electrons. When you see covalent, you could think in your mind the word share or sharing. Okay, so covalent bonds means that we share electrons. Okay, so this kind of breaks down the differences between elemental and compounds, and atomic versus molecular, molecular versus ionic. I'll let you go through this on your own if you're that type of person. What I find with these is sometimes if your brain doesn't quite work that way, it's more confusing. So we'll just kind of skip over it for now. But let's look at this. So on the left here we have propane. Okay, so propane is a molecular compound. Okay, propane exists of just carbon and hydrogen, so two nonmetals. Okay, so it's a molecular compound. On the right we have sodium chloride, something I've talked a lot about in this class so far. Okay, so this is made up of Na+ and Cl-. So that would be an example of ionic compound. Again, if you're not sure which is which, just look to see, first of all, does it have a metal? Okay, if it has a metal, most likely it's going to be ionic compound. If it doesn't, well, then it's going to be a molecular compound. Okay, so let's take a look at how to write chemical formulas. So first we're going to look at ionic compounds. Okay, or predicting chemical formulas, you could say. Okay, so first remember, ionic compounds are composed of nonmetal elements, or so a metal and a nonmetal element, or a metal and a nonmetal polyatomic ion. Okay, so easy enough. Ionic compounds are made of ions. Okay. So chemical formulas for ionic compounds are neutral unless otherwise indicated. Okay, so you will see sometimes ionic compounds that have a charge, but most of the time you're going to see them as being neutral. Okay, so here we have a question. It says, what is the molecular formula for manganese 3+ and oxide O2-? Okay, so we have manganese. Okay, it has a 3+ charge. Okay, so it has an oxidation of 3+. And oxide has an oxidation state of 2-. Okay, so in other words, sort of you can think of oxidation state as charge. We're not quite to oxidation state yet. Okay. So what we need to do is multiply the absolute value of the representative oxidation states to derive their molecular formula. Okay, in other words, so that's kind of a complicated way of saying you're going to take this charge, might give me that many oxides, and take this charge and give me that many manganese. Okay, so in other words, okay, so remember this. That's what we're talking about. Okay. So that's one way of predicting an ionic formula. Okay, and that's this. This is assuming that you know the charges of everything. Okay, so things like transition metals can have more than one charge. Okay, so it might not always be so easy to predict their molecular form or their chemical formula. Okay, so here we want to make sure that this all adds up to 0. In other words, that it's neutral. So +3 times 2 gives us +6. Minus 2 times 3 gives us minus 6 for a total of 0. Okay, so our charges are balanced. Okay, so this is probably a reasonable formula based on what we were given. Okay, so some basic charges, or in other words, oxidation states, okay, that we're going to look at for the various types of compounds here, the various elements. Okay, so your alkali metals, your group 1, so those are going to be 1 plus. Alkali earth metals, these is everything under, everything in the group with magnesium. Okay, so going to be plus 2. Your halogens, minus 1, 5A, minus 3, 6A, minus 2. Aluminum, plus 3. Hydrogen, plus 1 if it's with a nonmetal. Okay, and minus 1 if it is with a metal. Okay, so this is called a hydride. Or we would call this a proton. Okay, so if it's around a metal, it's going to take on more like a negative charge. If it's around with a nonmetal, it's going to take on a positive charge. Okay, so make sure you know this. And if you remember my 1, 2, 3, skip 3, 2, 1 thing, that's the same thing. Okay, so everything in the first column plus 1, everything in the second column plus 2. Skip over your transition metals and continue from there. Okay, so hopefully you know how to predict the charge of the things that we know what their charge is going to be. Okay, these are things we know. Okay, this is some polyatomic ions. Okay, this isn't all of them, but this is a pretty good list. So you need to know these because you need to easily be able to predict nitrate, for instance, something like that. If I tell you copper nitrate, you need to know that nitrate is a -1 compound, or hydroxide is a -1 compound. So if you learn these, I will try to always stick to, so for instance on the exams, I'll try to not give you anything that isn't on this list. Okay, so if you know these, you should be good to go. And if I don't, let me know. So if I pull one out of the blue on you, please do let me know. Okay, and if it is one of them that's not on here, suppose there's just some compound I want to use for a question, I'll give that to you. But if it's on this list, I expect you to know it. Okay, if we take a look at this, so we have things like chlorate and then perchlorate. Okay, so the per part is always going to mean that it has one more of something. And in this case, it's oxygen. Okay, so we go from ClO3 to ClO4 minus. Okay, so we've increased the oxygen, the number of oxygen, so we get this, we're getting per. Okay, so we go from chlorate to perchlorate. And notice that if we go down in oxygen, so from 3 to 2, now we end in ite, so chlorite. Okay, and if we go down even one more oxygen, we go to hypochlorite. Okay, so that means we've even lost even one more. Okay, and you'll see that a little bit in this list. So nitrate to nitrite. Okay, so there's some similar ones, but make sure you get to know these. So hydrogen sulfate, hydrogen sulfite. Okay, so get to know these and make sure that if it's on this list, you can predict it pretty easily. Things like carbonate, nitrate. Okay, you need to know these. Okay, it's going to make your life so much easier. Okay, so how about naming them? So now we know that if we're given the charges of two atoms, we can make an ionic compound from them pretty easily. Okay, so how do we name them though? Okay, when it comes to naming ionic compounds, it's not that bad. Okay, so if we want to name ionic compound, okay, so the first thing you're going to do is we're going to name the cation. Okay, so for instance, magnesium, potassium, copper. Okay, now we'll get into the transition metal elements, and those are a little bit different. Okay, but for now we're just talking about your basic alkaline earth metals. So the important thing here is that things like magnesium, potassium, calcium, they only have one charge state. Okay, so there's no need to indicate what the charge is. Okay, so what we're going to do is we're going to first name the metal. And then we're going to name the nonmetal. Okay, but the important thing about this is, or the kind of trick to it here, is that we're going to turn the nonmetal ending to ide, IDE. Okay, so if we want to name a metal and a nonmetal, okay, so we have an ionic compound. First, name the metal cation, so for instance, magnesium, potassium, and then name the base name of the anion. So what I'm talking about here, I could say fluorine. Or let's not use fluorine, let's use chlorine. Doesn't really matter, but okay. What I'm going to do is I want to change this ending. So chlorine becomes chloride. Fluorine becomes fluoride. Iodine becomes iodide. Okay, and that's really all there is to it. So some examples here. We have MgCl2. Okay, so first thing we're going to do, name the metal cation. So in this case, it's magnesium. Okay, and then write the base name of the anion. So this time it's chlorine. So change the ene to ide. Okay, so we have magnesium chloride. Okay, well, what if we have a polyatomic ion? How do we do it then? Okay, it's very similar. Okay, so first name the metal, so potassium. And now what we want to do is just write the name of the polyatomic ion. So this is why I say we need to know these. I need to know what nitrate is. Okay, so the name for this, KNO3, is just potassium nitrate, because anyone studying chemistry will know what nitrate is. Okay, so I know the charge of nitrate already, and I know the charge of potassium. So all the information I need is in this name. Okay, so just remember alkalis, +1, alkaline earth metals are +2. Okay, and what we're trying to say here is that these oxidation states, these are known. So I don't have to tell any more information about it. Okay, so I don't have to indicate their charge. So this is why it says the charge is not indicated. There's just no reason to. Anyone studying chemistry will know that potassium is +1. Okay. So here's just some common anions. Here you see your halogens, but then you get into oxygen, so keep the OX from oxygen, make it oxide. Sulfur becomes sulfide, nitrogen becomes nitride, and phosphorus becomes phosphide. Okay, so these are just the basic ones. Make sure you know these, but really all you're doing here is chopping off the ending and making it ide. Okay, so go over these and make sure that you know them, and you'll get enough practice that these will become really second nature to you. Okay, like now for instance. Okay, so it says name the compound CaBr2. Okay, so give the video a pause. I'll give you a couple seconds. Go over this one. Try to come up with the name for this compound, and then we'll go over it together. Okay, so let's take a look at this one. So they give us CaBr2, and they want us to name this. Okay, so the first thing we're going to do, just name the metal. I almost said nonmetal, but you name the metal first. Okay, so the metal here is calcium, Ca. Okay, so that's right there in group 2. CaLCium. That's all we need to do. Calcium. Okay, now we want to name the nonmetal. So here we have bromine. Okay, you don't have to write it out like this every time once you get the hang of it. Okay, but then we want to change the ending. Okay, so bromine becomes bromide. Okay, so the name of our compound is calcium bromide. Okay, so like I said, you don't have to write out bromine and change it to bromide every time on your paper, just until you get the hang of it. So you could even just erase it. Like so, instead you could do this. So you could write out bromine, then just erase it and write bromide. Okay, but once you get the hang of it, you'll be doing it in your head, and you don't have to write that down. So in other words, I don't have to think about that. I wouldn't have to think to call this compound calcium bromide. It would just happen. Okay. But until you get the hang of it, you might want to write it out if that helps you. Okay, so see what they say here. Cation is calcium, the anion is bromine, which becomes bromide. The correct name is calcium bromide. So just like we said. Okay. Now here's another one. It says name the following ionic compounds. Okay, same thing here. Give this one a try, and then we'll talk about it. Okay, so the first one we have sodium. So we have NaI. We have sodium. We have iodine. Okay, so first thing, just write the name of the metal. So sodium. Okay, and then we have iodine, which becomes iodide. So Okay, the next one, Mg3N2. Okay, so it doesn't matter that we have 3 and a 2. Okay, because remember what we just talked about is that we know what the charge of these are going to be, so there's no need to indicate in the name what the charge is or how many of them there are. There's no need. Okay, so here we write magnesium. We have nitrogen, which becomes nitride. Okay, next one, aluminum. Okay, then sulfur becomes sulfide. Okay, so we have sodium iodide, magnesium nitride, aluminum sulfide. So hopefully you got those right. These are, I don't think, too tough. You're just really just changing the ending of the nonmetal. Okay, we can check our answers. And you should have this in your slides. Okay. Okay. So now we're going to talk about naming transition metal compounds. Okay, it's a very similar process. Okay, there's just one extra sort of wrench in this process that makes it a little bit different. Okay, so if we're talking about a metal and a non-metal, in this case we're talking about a transition metal. Okay, so if we have a metal coming from that transition metal group, transition elements, it gives us an extra little wrench in our system here. Okay, so what we're going to do is we're going to, again, just as we did before, write the name of the metal, followed by the nonmetal. So the issue is that certain elements, especially transition elements, can have more than one oxidation state. In other words, they could have a different charge. So they could be +1, +2, +3, +5. There's lots and lots of charge states that transition metals can have. Okay, some more than others, and some are more prone to others than to certain oxidation states than others, and that has to do with some stability and things like that we don't have to get into. And others can be a really wide variety. Okay, so the issue here is that we have to indicate the charge of the metal because it can have more than one charge. So it's not like magnesium. It could have a different, so magnesium is only going to be +2. Well, something like manganese, like for instance here it's +4, but it could be other things as well. Okay, so the rest of it is the same. I'm going to change the ending of the nonmetal to "ide." Okay, the only thing we're changing here is that we have to indicate the charge of the metal using a Roman numeral. Okay, so name the metal, so name of the metal. Then, in parentheses next to it, you're going to give the charge with a Roman numeral, and then base name of the nonmetal, and change the ending to "ide." That's it. Okay, so very, very similar. So here we have MnBr4. Okay, so if I didn't know, so here I'm not being told what the charge of manganese is. So how do I know that? Well, the way I know that is because I know what the charge of bromide is. So I know that bromide is -1. Okay, and I know that I have 4 of them. Okay, so I'll actually put a 1 in here. So it's -1. So for a total of -4. And what did we talk about? We said that these ionic compounds, the charge needs to be balanced. Okay, so I don't have a charge here. If I did have a charge, you might see it written like this. Something like that. Okay, or you may see it in a block like this with a minus sign on it. Okay, but I don't have that, so I just have a neutral compound. So that means that manganese has to balance out this +4, or -4, excuse me. Okay, so what am I saying? That means that manganese has to be +4 to give me total charge of 0. Okay, so that's exactly what I've done here. So manganese, and then the Roman numeral tells me it's +4. Okay, and I know it's +4 because it's the metal. Remember that the metals, generally speaking, take on the positive charge. And then bromide. Okay, I know what bromide is. So I don't actually have to say that I have 4 bromides. But I do need to indicate the charge of manganese. And same thing, okay, so next one we have iron oxide. Well, which iron oxide? Well, iron 3 oxide. Okay, we're going to do it just the same way. So I know I have 3 oxygen, each with a -2. Okay, so I have 3 oxygen, which are all -2, which gives me total -6. Okay, so I need to balance that with a +6, but I have 2 iron, so I'm going to divide that by 2, so each one has to be +3. Okay, so here I have iron 3 oxide. Okay, and the last one, SnF2, that's tin fluoride. And then I have 2 fluorines, each with a or fluorides -1, each one is a -1. Okay, so this is tin 2 fluoride. Sorry, I kind of got cut off there. That's their answer there, though. Tin 2 fluoride. Okay, so the only thing we've changed is that now, since the charge of the metal could vary, we have to indicate it with a Roman numeral. That's it. Okay, so here's some common transition metals and their charges, along with their names. Okay, so iron, for instance, could be iron 2 or iron 3, okay, indicated with the Roman numeral. And notice there's even one more way to indicate this, so ferrous and ferric. Okay, so ferrous is iron 2, ferric is iron 3. This is an older way of naming these compounds. It's not really used as much anymore, but maybe you've heard of like ferric iron before, or ferric metal before. Okay, this is what we're talking about. So the us will always be the lower, and the ic will always be the higher. So, for instance, cobalt here, we have +2 and +3. Cobaltus, +2, cobaltic, +3. Okay, these are not used all that often anymore. Okay, but it's good to know. So I could ask you a question, for instance, what's the charge of ferric iron? Okay, so you want to be able to tell me that it's +3. Okay, but a little bit more of a traditional way of naming it. That's not really used. Nowadays, we use the Roman numerals. Okay, but if you were to talk to a chemist that's been doing it for a very long time, they're probably going to be more comfortable talking with ic and us, whereas someone younger is going to be more comfortable talking about iron 2, iron 3. Okay, but just make sure you know. And so back to my point here is that you see that a lot of these can have multiple charge states. They've only listed 2 here just to illustrate the ic and the us, but there can be others besides this. For instance, cobalt can also be cobalt +1. Okay, so big part of my PhD project was working with cobalt 1. It's very unstable, okay, but it does exist. Okay, so just know that there's more than just what you see here. Okay, but just get a feel for these. Make sure you understand what they are. So I've given the polyatomics again here just for reference. Let's see, is there anything I really need to say here? No, I don't really. I think I just gave them to you for reference. Okay, here we go. So it says name the following compound, and we have PbCl4. So I'll give this one a try. See if you can name it. Okay, remember, just indicate the charge using a Roman numeral. See what you come up with. Okay, so just like we did before, I'm going to write the name of the metal. So this time we have lead. Okay, and when we have chlorine, chlorine becomes chloride. And we have 4 of those. So now we need to figure out what's the charge on lead. Okay, well, each chloride is -1 times 4 gives me -4. Okay, I only have 1 lead, so 1 lead needs to balance out -4, which makes it +4. Okay, so I'm going to indicate here with the Roman numeral, lead 4 chloride. That's it. That's all you have to do. And you could easily go back the other way. Okay, so if, for instance, I was to give you this instead. Okay, so what if I just gave you the name lead 4 chloride? Okay, so you start out by writing lead. Okay, easy enough. But now I need to take the fact that I know this 4 tells me that this is +4. Chloride I know is -1. So I have to balance these two. So I could do it this way. I could either do it logically or I could do it this way. It's PbCl4. Okay? So make sure you can go either way, backwards or forward, with the naming conventions. Okay, so here I have some of that written out for you. Okay, so I'll give you a second if you want to pause and read this. It says just what I've already told you. Okay, so give a try naming these 3 ionic compounds. So the first one we have SnF2. So we have tin and we have fluorine. Okay, so first we'll write tin, Tin. Okay, then we know fluorine becomes fluoride. Sorry, fluorine, not fluorine. I always do that. Okay, now we need to figure out what's the charge on tin. Well, I have 2 fluorines, 2 fluorides, both -1. I have 2 of them. Okay, so it's going to be tin, 2 fluoride. And there should be a space between the Roman numeral and the nonmetal. Okay, so make sure you put a space in here. Okay, next one. So we have iron and we have nitrate. Okay, so here we'll write iron. Okay, now this is where knowing these polyatomics comes in, because I know this is nitrate, but I have to know what the charge is. Well, it's -1, of course. Okay, so I will just write nitrate. Remember, you don't change the name of your polyatomic ions. Now I just have to indicate what charge iron is. There's 3 nitrates, so this is going to be iron 3. Okay, so remember, if you're not sure, you can come back to this list of your polyatomics. So where's nitrate? NO3, nitrate. Okay, the next one we're going to look at is phosphate, PO4. That one's going to be 3-. Okay, just as long as we're here, we might as well look at that because we weren't sure. Doesn't want to let me erase those, that's fine. Okay, so I have copper. Okay, then I have phosphate, so just write phosphate. Okay, now I need to figure out what the charge is of copper. Okay, so these other 2, I've only had 1 of the metals. But now I have 3. Okay, so it makes it a little bit trickier. Okay, but I know phosphate is -3 times 2 gives me -6. Okay, so if I just divide this by 3, since I have 3 coppers, it gives me -2. So that tells me how much charge each copper needs to balance. So if each copper has to balance -2, then each copper should be +2. So here we'll just indicate that like this. Okay, so you have copper 2 phosphate. Okay, we can check our answers. So tin 2 fluoride, iron 3 nitrate, copper 2 phosphate. Okay, I'll just get rid of that so you can see everything. Okay, so that's all there is to it. So just determining what the charge is of the metal, indicate it in Roman numerals. If it's halogen or something like that, change the ending to "ide." If it's polyatomic, just keep the name of the polyatomic. So notice here, this is nitrate. So if we have just N, it becomes nitride. Okay, so that's why we don't mess with the endings of our polyatomics, because that would be confusing. Okay, so for instance, if I had phosphide, that would be just a phosphorus, but phosphate is PO4. Okay, so that's why we do that. Just keep everything straight. In this next section, we're going to talk about hydrate compounds. Okay, and we're going to talk about naming hydrates. Okay, and then after that, we're going to get into naming acids, and they're very, very similar. Okay, and then from there, I think we'll probably stop for the day. I think we'll finish it with naming and pick up next time. Okay. So what is a hydrate? So here we have copper sulfate. And copper sulfate can exist in 2 ways. Okay, it can exist as either the hydrate or as an anhydrous compound. Okay, and the difference between the 2 is that one has water associated with it and the other doesn't. Okay, so when you see this dot, the center dot, what that means is that the thing next to it is not quite bonded, but it's very closely associated, meaning they're not going anywhere very easily. Okay, so they're there. So it's almost like them being bonded, but it's just like an association, more is how we say it. Okay, and the difference between it being permanently bonded and it more being a loose association or a close association, you could say, is that for one thing we can do is actually to dry it using heat. Okay, so we call this driving off the water. Okay, so if we heat something up, we can say that we're driving off the water. There's actually instruments you can use to do this and actually measure how much water is there if you're interested in that sort of thing. Okay, or some compounds in particular actually change color, and copper sulfate is one. And this is pretty common throughout the transition metals, is forming hydrates like this at particular oxidation states. Okay, so here we have copper sulfate. The anhydrous compound is all of this that's white. Okay, so that means that we've driven the water off. We've removed the water. So it starts out as this blue compound, so indicated here or shown here. And if I were to put this in a small test tube or something similar, or a beaker or anything like that, okay, and put it over a Bunsen burner or even a hot plate. Okay, you could actually even do this in a solution, which is kind of interesting. Okay, so if I was to heat this, what happens is this water will be removed. So I go from the hydrate compound to the anhydrous compound. So if, for instance, I'm interested in making a copper compound, and suppose I want to make, for instance, a copper 1 compound, or silver 1 compound, or a gold 1 compound. What I don't want in my reaction mixture is water. Okay, and if I use a copper source that has water with it, well, that's going to ruin my reaction, for instance. Okay, so if I don't want any water around, maybe I want to dry it. So I'll heat it up. Now, most likely in the lab, you would actually buy anhydrous. Okay, but if maybe you didn't have that around, you could dry it this way. And what's nice is you get this nice color changing. Okay, and the point is, we go from the hydrate to the anhydrous compound. Okay, and the point we're getting to here is how to name these. Okay, so hydrates are ionic compounds containing a specific number of waters for each form of the unit. It's kind of funny in chemistry you say waters, meaning if you have more than one water. Okay, it's kind of a unique thing about talking about chemistry. Okay, so water of hydration is often driven off. So again, this is like a jargon term, driven off. It just means removed by heating. Okay. So in the formula, the attached waters follow. So again, that's this part, just like we talked about. Okay, so how do we name these? In the name, the attached waters are indicated by a prefix and then the word hydrate. Okay, so after the name of the ionic compound. So just like you would name a regular, so cobalt chloride, copper sulfate, anything like that, name it the exact same way, but now we're going to add the hydrate term to it, or the hydrate portion to it. So for instance, here I have cobalt chloride, so cobalt 2 chloride, and I see that it has 6 waters attached to it. So this is the prefix scale that we're going to use. So hemi, mono, di, tri, tetra, penta, hexa, hepta, octa. Okay, so if you don't know these already, you're gonna get to know them. Some of them are pretty self-explanatory. Octa, like octagon. Okay, so a lot of these you probably already know from geometry. Some of you might not. Try from triangle, or similar to triangle, not from triangle. But so then figure out what prefix you need to use. So here I have 6, so I need to use hexa. Okay, and then I just put the word hydrate. So this becomes cobalt 2 chloride hexahydrate. Okay, and that's all there is to it. Okay, so the next one I have calcium sulfate, and it has 1/2 water associated with it, so that happens sometimes too. So write out the name calcium sulfate just like you would before, so no need to indicate charge here since we're dealing with calcium. Okay, then we have 1/2, which is hemi. Let me go back. Okay, so hemi, so this becomes calcium sulfate hemihydrate. Okay, so just make sure you get to know these prefixes. We're also going to use these in naming molecular compounds, so good to just go ahead and get to know them. Okay, so here they want us to write the formula of magnesium sulfate heptahydrate, and then they want us to name a nickel compound. So based on what we just talked about, give the video a pause and give these a try. Okay, so for the first one, they've given us magnesium sulfate heptahydrate. So magnesium, it's in our group 2, so we can only have one charge state here. We have sulfate along with it, so we can go back to our polyatomic ions real quick. Find sulfate. Okay, so sulfite, sulfate. So it's 2 minus. Okay, so once you get to know those, you won't have to keep referring back to a table like this. But until you do, there's nothing wrong with that. Okay, so sulfate 2 minus. Good. SO4 2 minus. Okay, we talked about this already. Let's get back to where we were. Here we go. Okay, so I kind of gave the answer away, but that's okay. Okay, so sulfate we said is SO4, and we said it's 2 minus. So what does that mean? That means that every magnesium has to balance out 2 minus. Well, we know magnesium is already 2 plus, so easy enough. So we say MgSO4. Okay, not too bad. Sorry, that's a G, believe it or not. Okay, there we go. So this is already balanced. Now we just need to write our heptahydrate. Okay, so hepta, so if we go back to our table there, what's hepta? Hepta is 7. Okay, so we're going to write our center dot and write 7 H2O. And that's it. That's all there is to it. Let's check our answer real quick. So 7 H2O. MgSO4, 7 H2O. Good. Okay. So let's try the second one. Let's get rid of this for you. Okay, so what is the name of NiCl2 6H2O? So first we know it's nickel. Sometimes my K's look like an L and a C back to back. It's EL, right? Duh. So nickel, and we have 2 chlorides associated with that, so they're both minus 1. So it's going to be nickel 2 chloride, so just like before. And then we have 6, which is hexa. And we'll write hydrate. Okay, check your answer, nickel 2 chloride hexahydrate. So we got it right. Okay, so hopefully you're getting these. Hopefully those are not too tough. Okay, so I'll go back for just a moment in case you needed those answers again. Ooh, my computer is not happy with me right now. Okay, so just in case you need the answers again. Okay, let's look at the next part. So now we're going to get into naming molecular compounds. So we'll name molecular compounds, and then we'll name acids. Okay, very, very similar. Okay, there's not a whole lot of difference between all these different namings. It's just when to use what is all you really, that's kind of the thing. Okay, so first we're going to name the most metallic of the nonmetals first. So what do I mean by the most metallic? What I mean by that is the furthest to the left. Okay, so the things that are closest to the metals, that's going to come first. So for instance, we would name carbon before oxygen. Okay? So change the ending of the nonmetal to IDE. Okay, so this should be in quotes here. Okay, so the ending of the nonmetal. Okay, we're going to indicate the number of atoms of the nonmetal by the Greek prefix, and again, we're going to use our mono ditri. Okay, so for example, well, I guess nonmetal doesn't have to be in quotes there. being a little silly. Okay, so for instance, P2O5. Okay, so we're going to want to name each nonmetal. Okay, so same naming conventions happen here with the oxygen to oxide. The difference is now we're going to add the prefixes. So P2O5 becomes, there's 2 phosphorus, so it becomes diphosphorus. And you just keep the name the same. Okay, then oxygen becomes oxide. There's 5 of them, so it becomes pentoxide. And you'll notice we drop the A. So generally speaking, if there's 2 vowels back to back, you'll drop one of them. So in this case, we drop the A. Okay, then we have carbon monoxide. Okay, so CO, carbon is more metallic than oxygen, we said. And notice we don't write monocarbon. So if it's the first one, generally we leave out mono. So we only put mono in the second half. Okay, so here we have carbon, and then we have 1 oxygen. Oxygen becomes oxide. And we give it mon because there's only 1, so it becomes carbon monoxide. And again, notice we drop one of the O's here. Okay, so we don't write monoxide, right? So we're going to write monoxide. Okay, so prefix, name of the first nonmetal element, prefix, base name with the ending change to IDE, and a prefix. Okay, so let's look at these together. So the first one, SO2. Okay, so I'm going to write sulfur. Okay, so I only have 1, so it's just going to be sulfur. And then I have 2 oxygen, so I would say dioxide. So sulfur dioxide, where the di gives me 2. Okay, here I have SiI4. So I have silicon. Oh, that's not right at all. Sorry, I'm talking and writing, so sometimes hand gets a little bit away from the mind. So I have silicon, and I have 4 iodides, so this would be tetra. Tetra is 4, so silicon tetraiodide. Next one, sulfur, and there's just 1, so I don't write mono. Okay, so sulfur, and there's 6 fluorines, so I'll write hexa. Fluorine becomes fluoride. Okay, next one, CS2. And remember, for all these, we're picking the most metallic one, but they're generally written that way as well, so it's not too tough. Okay, here I have carbon. Remember, I just have 1 carbon, but I don't write carbon mon, or mon carbon. Just leave it as carbon. 2 sulfurs, so I would say disulfide. Okay, next one. Again, I have SiC. So here's one where I have to kind of make a judgment call on which one is more metallic. So carbon and silicon are in the same group. So how do I pick between that? Well, I'm going to pick the one that's lower. That's going to be the more metallic one. And in fact, silicon is a metalloid, so it's not too bad. Okay, but just remember, if you point arrows right and up towards fluorine, further away from fluorine, those will be more metallic. So whichever one is further from fluorine, basically. Okay, so I'll write silicon, 1 carbon. So this one actually is just carbide. You don't write monocarbide. Okay, and there's some of these that are just sort of known. So that's just a traditional way of naming. So for instance, carbide, you don't write mono. Okay, so let's check all our answers here. Okay, so you see carbide, or carbon just becomes carbide. We don't ever write monocarbide. And again, that's just from traditional ways of naming. You'll see some things that are done that way. And you basically just have to know them. That's really the only way. There's really no rhyme or reason to it other than it's just been traditionally done that way. Okay, so now give these a try of naming by yourself, and we'll go over them together. Okay, so the first one. So we have carbon. We just have 1 of them, so we just write out the word carbon. Okay, remember, if we're going to compare carbon to oxygen and pick the more metallic, so we're going to pick carbon because it's to the left, it's closer to the metals. Then we have 2 oxygen, so we'll write di, and we'll write oxide. Okay, easy enough. Next one, so we have sulfur and bromine. So again, we have to compare these. Okay, so bromine is obviously a halogen. Sulfur is a lot closer to our metals, so sulfur is definitely going to come first. So sulfur, there's only 1, so I just write sulfur. And then I have 6 bromides, so this is going to be hexa. Bromine becomes bromide. So I end up with sulfur hexabromide. Next one, I have I2F7. Okay, so remember, I'm going to try to pick the one that's furthest from fluorine. So obviously iodine is going to be more metallic than fluorine. So we'll write di. And this is one where you'll see people sometimes leave off the second I, sometimes you won't. Diiodide, and then we have 7, which is hepta, and fluorine becomes fluoride. Sorry, I misspelled fluorine again. Okay. So let's double check our answers. Yep, so we got those all right. So carbon dioxide, sulfur hexabromide, and diiodide heptafluoride. Okay, so hopefully you're getting those. This is just knowing your prefixes pretty much. You know what I mean? All right, so it says, write formulas for the following compounds. So this time we have the name, and they want us to go backwards. So give that a try. Okay, so the first one we have sulfur trioxide. So sulfur, just S. And there's no indicator about how many, so that tells me we just have 1. Okay, trioxide means we have 3, so sulfur trioxide. Okay, next one, dinitrogen tetrahydride. Okay, so dinitrogen means we have 2. Tetra means we have 4. 4 of what? 4 hydrides, so N2H4. Next one, diarsenic trisulfide. So how many do we have? We have 2. 2 what? Arsenic. Okay. And then trisulfide, so we have 3 sulfides. Okay, so that's it. Sometimes I think some students have an easier time going from name to formula, and some students have an easier time going from formula to name. That's just sort of luck of the draw and like the way your brain works, kind of. But hopefully you'll find a way to make it easier to go either way for yourself. But make sure you can go from name to formula or from formula to name. That's going to be real important. So I could ask you either way. Okay, check our work here. SO3, N2H4, AS2, S3. So we got them right. Okay, so before we get into naming acids, so I just remember what we were just talking about. This was all naming molecular compounds, so 2 covalently bonded atoms. Okay, so first we talked about ionic compounds, then hydrates, and then molecular compounds. Okay, but this slide, what I want to mention here is just that we also have common names for some chemicals. So I know this is fairly obvious, but I think it's worth mentioning. So something like water, for instance, H2O, okay, commonly called water. NH3, ammonia. Bleach is actually NaClO. Okay, so, and lime, so like lime you would put in your garden or something like that, CaO. So the point what I'm trying to make here is that just remember that things we commonly know in the world, like bleach for instance, has a chemical formula. Okay, your toothpaste has a chemical formula. You know, these things in our daily lives all come back to chemicals. That's kind of what I'm trying to say here. So just keep in mind, there are, of course, common names for chemicals as well. Okay, so we'll finish up on this for right now. So we're going to name acids. Okay, so what is an acid, first of all? Okay, so an acid, at least according to one definition, releases hydrogen ions, H+, when dissolved in water. So for example, HCl gives us H+ and Cl-. What are the characteristics? They're sour, they have low pHs. Okay, and we have two types of acids. Okay, so this is what's important for the naming part of this. We have binary acids. These only have two elements. So for instance, HCl, that's a binary acid. So they have an H+ and then a nonmetal. Okay, and then we have oxyacids. Okay, so these are things that have a cation, so H+ cation, but their anion is polyatomic. Okay, and it generally contains oxygen atoms. Okay, so it's important to make this distinction and make sure we understand this now, because the way that we name these is different depending on if it's a binary acid or an oxyacid. Okay, so let's take a look at that. Okay, so if I'm going to name an oxyacid, we're going to need to change the "-ide" and the "-ate" endings. Okay, so "-ide" and "-ate" change to "-ic." Okay, so if I make an acid from nitrate, it becomes nitric acid because of the "-ate" becomes "-ic." So "-ate" to "-ic." So if I have chloride, so "-ide" also goes to "-ic. So this would be hydrochloric acid. So "-ide" to "-ic. "-ate" or "-ide" and "-ate both change to "-ic. Okay, and the reason I'm sort of talking about this is because if we have "-ite" instead, so when we have nitrite, that gets changed to "-us." So "-ide", "-ate" to "-ic, "-ite" to "-us." Okay, so nitrite becomes nitrous acid. And the way that you can remember this is kind of silly sounding, but it will help. So you can say 8-idic itis. So I came down with a case of 8-idic itis. Okay, it'll help you just remember. 8 and "-ide" to "-ic, "-ite" to "-us." Okay, so we're going to need to know that for naming acids. So we need to know the difference between binary and oxyacids. We need to know the difference between, or how to change the endings, 8 and "-ide" to "-ic, "-ite" to "-us." Okay, so make sure you get those down. I gave you the polyatomics here again just for convenience. Okay, so let's take a look at some of these. So the first thing we have to do when we're naming an acid is you first need to establish whether it's a binary acid or an oxyacid. And the way you're going to do that is you're going to look at it and you're going to say, okay, does it have more than two atoms? So more than hydrogen and now it could be multiple hydrogens, by the way. It could be H2 or something like that. Okay, but if I only have two types of atom, that's binary. Binary meaning two, of course. Okay, if not, if I have something like a polyatomic with an oxygen, that's an oxyacid. Okay, so the next thing I have to do, figure out what the polyatomic is, if I have a polyatomic. So here I have my first one, HClO2. Okay, so obviously that's not a binary acid. So I come back to my list of polyatomics. So what am I looking for? I'm looking for ClO2. Okay, so I'll come back. So ClO2, so chlorite. Okay, remember, "-ite" to "-us." Okay, so the first one would be what? Chlorous acid. Notice I don't say hydrochlorous acid, I just say chlorous acid. Okay, the next one, HF. So now this one is a binary acid because it only has two things. Okay, so the first thing I'm going to write is hydro. Okay, so when we're naming a binary acid, we write hydro. Then fluoride becomes fluoric, remember? "-ide" to "-ic. So this becomes hydrofluoric acid. Okay, the next one, acetic acid. Okay, so now we have a name. We want to go to a formula. Okay, so we have to recognize first this is going to be an oxyacid because, why? Because I have to recognize that this is a polyatomic ion. Okay, so what am I naming my formula? So this is just acetate with a hydrogen stuck on it. Okay, so that's all we do there. So just make sure you can recognize polyatomic ions, and to make it an acid, you're going to want to add an extra proton or an extra hydrogen. Hydrochloric acid, I see the word hydro, so I know it's a binary acid, so chloric is chloride, so just HCl. Okay, this last one is sort of an interesting one because there are acids that aren't binary or oxy. So they can just act as an acid. Okay, so NH4, for instance. This is just the ammonium ion. Okay, so some things are named that way as well. Just keeping that in mind. So if you encounter NH4, understand it can act as an acid, and we call it the ammonium ion. Okay, so try to name these three acids real quick. Okay, so go ahead and give me a pause and try to name these acids. Okay, so the first one, we have H2S. Okay, so this is going to be a binary acid. And remember, to name binary acids, we start out with the word hydro. Okay, S, so sulfur. Sulfide becomes, so I to ic, so sulfuric, hydro, sulfuric acid. Okay, the next one, I see it's oxyacid. Okay, hydrosulfuric acid. So the next one, I see it's an oxyacid. So I want to start out, by figuring out what polyatomic ion I have. Okay, so go back to my polyatomics real quick. So I have ClO4. So let's go back. ClO4, perchlorate. Okay, so how do I name this one? So remember 8 to ic. So this would be perchloric acid. Let's check our answer. Perchloric acid. Perfect. Okay, the next one, I have HNO2, again another oxyacid. So let's go back. Okay, NO2, nitrite. Remember, ite to us. So what would this be? This would be nitrous acid. Okay, let's just check those, and we're right. Okay, so if this was HN, we would write hydronitric. So it takes a second to think about these sometimes because they're not commonly used. But yeah, so that's just to avoid the confusion. That's why we named them differently. Okay, so the next one. Okay, give these a try. So now we have the name, and they want us to give them the formula. Okay, so the first one, I have chlorous acid. So remember, so it's ide and 8 to ic, ite to us. Okay, so us would be chlorite. So let's go back to our list of polyatomics here. So chlorous is what we want. A chloride, I mean. So ClO2. Okay, so this would be first ClO2, and we'll put a proton up front or a hydrogen up front to make it an acid. Okay, so H plus and ClO2 gives HClO2. Next one, phosphoric acid. Remember, ide and 8 to ic. Okay, so what do we have? We have H plus and PO4 3 minus. Remember, just go back and check your polyatomics if you're not sure. So what do we end up with? H3PO4. Why the 3? So make sure we pay attention to this. So remember, this polyatomic is 3 minus. Okay, and I'm writing the bars there just to indicate that's what I'm talking about. Okay, so 3 minus. So that means I need 3 H plus to balance out the 3 minus. Okay, so that's why we put 3. Next one, hydrobromic acid. Okay, so we have the word hydro, so we know it's binary. Bromic, we know it's bromide. Acid to tell us it's an acid. So this is just H plus and Br minus, so just HBr. Okay, so I think that's a good place to stop with this video. Okay, so I will put up some practice of those for you guys, but make sure you get your naming down pat, and we will finish off this chapter next time.